So let's talk a little bit about the moon as it orbits the Earth. Um, so this is a picture of the Earth with the moon in various positions around it. If you remember the scaling on this, the sun is 400 times farther away than the moon. And so we can view the sun as just way off the screen to the right in this picture somehow. And the moon is kind of close to the Earth. And the only thing that's a little awkward about this is, I don't know if you remember, a while ago we had, I think it was in the last chapter, we had a relative size scale of the Earth and the moon. The moon is about 30 Earth diameters away. And so it's this picture is a way bad scaling, very poor scaling, but it's just doing it for illustration purposes so that we can see kind of what's going on here. So if you look at how the Earth and the moon are lit by the sun, the side of the Earth and the moon both that's facing the sun is lit and the other half is dark. And so regardless of what position the moon is in, it looks the same when you're looking from where we're looking at outside the screen. But what these pictures are on the outside is what the moon looks like in these various positions, A, B, C, D, E, F, G, and H, if you were on the Earth in this picture. If you look at position A, the moon, you're just seeing the backside of the moon, and so this picture over here is what you're seeing from Earth. It's called a new moon, and you're seeing the dark side, none of the lit side. As the moon orbits the Earth, remember it takes the Earth about a month, so about 4 weeks to orbit the Earth. And so this is maybe 3 or 4 days later. Now the moon is over here. You're somewhere on the Earth where you can see the moon. By the way, about half of the people on Earth can see the moon at any time, right? The half who's on the same side. And so now you can see a little bit of the lit side from the Earth. And so you see what we call a crescent moon. When it's after it's new and the lit part is getting bigger, it's called waxing. So this is a waxing crescent, right? And then when the moon when the moon and us and the sun make a 90-degree angle, so the moon is in this direction and the sun is in this direction, we call that first quarter because it's a quarter of the way around its orbit, and that's about a week. And so we see a moon that's half lit and half dark. Right, and we call it quarter again because it's a quarter way around the orbit, right? And then a few days later, 3 or 4 days later, now it's called a waxing gibbous. Gibbous just means fat, and so it's the lit part is getting pretty close to full. And then when it's on the back side of us now, we're seeing the side that's completely lit. We call that a full moon. And now we're starting to see some of the dark side again, and so now we call this waning gibbous. Waning means getting smaller. And then third quarter, and then waning crescent, and then back to new again. And so the moon marches around these phases as it goes around the Earth. And so let me go back and draw these pictures as well. So this is the direction of the sun over here, and so sunlight's coming from this direction, right? And here's the Earth, right? And so here's the moon going around the Earth, just like a little bit ago we had the Earth going around the sun. And so if we start with a new moon, again we just have a dark side, and so this is a waxing crescent. And then all the way around here to full, right? And then again, this side is lit, and so third quarter. Here's first quarter. So new, waxing crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent, and back to new again. Right. And so if I draw the picture of the Earth going around the sun, so now here's the sun, and here's the Earth's orbit, right? So here's the Earth. And now I'm going to draw the moon's orbit. Again, this will not be a scale drawing because I can't do a scale drawing this way. So this is a new moon, right? So this is the moon, and this is the new moon. And so the time for a new moon is the time for one of the moon's orbits is the time between new moons. The period of the moon is the time between successive new moons. And so you might think, well, that's just one orbit. Well, again, we're back to that synodic sidereal thing, because now the Earth has gone to here, right? And if we were to say to just one loop of the Earth, that would be here, right? For it to have gone around, for it to have done one complete loop, it would be to go back to this position, or to this position, I guess, more accurately. Right? But that's not the new moon. The new moon is when the moon is in the direction of the sun, and so the moon has to rotate an additional distance, right? And so the synodic period, so the synodic period is about 29.5 days. The sidereal period is about 27.3 days. That would be, the sidereal period is the time it takes to do one complete loop of the Earth relative to space. The synodic period is the time it takes to do from new moon to new moon, or from full moon to full moon, whichever. But it's the synodic period is always its relative position relative to the sun. The sidereal period is just its position relative to space, and so the sidereal period is always a little shorter. So I'll put up a graphic of these, but you should be able to identify, if I just throw up this picture without all those views on the outside, if I just have the Earth's and the inner ring of the moons there and say position B, you should be able to tell me whether that's a waxing crescent or a first quarter or a waxing gibbous and so on. If I just give you this diagram without the guys outside and without the words there, you should know that H is a waning crescent, G is third quarter, and so on. So let's talk a little bit more about how the moon moves. Here is a picture of the moon's orbit. So the moon orbits with one face towards the Earth at all times. So we never see the back side of the moon. The face of the moon that faces the Earth is always facing the Earth. So what we really see is the bottom picture here, where the same piece is pointing towards the Earth the whole time. And what that means is that the Earth is rotating, the moon is rotating once on its axis every time it orbits, exactly the same rate every time it orbits the Earth. So that's why the moon always looks the same when you see it on a clear night, because we're always seeing the same side. And so some people will say that means the moon isn't rotating. Well, if the moon wasn't rotating, then you would see what we see in the top picture, which is, if it wasn't rotating, it would always be pointing towards that crater, or whatever it is, would always be pointing in the same direction. So sometime we would be seeing the other side of the moon, or the side of the moon, or the top of that crater, or whatever that is, and then the other side, and so on. And so the moon rotates in such a way that it keeps the same face towards us at all times. That's often called synchronous rotation. Ooh, not that. Sorry. There we go. So hang on a second. Let me just pull this up. That's why we needed time zones. So phases of the moon. The moon orbits the Earth, always keeping one face towards the Earth. This means that the moon is making one rotation on its axis for every orbit it does around the Earth. This is called synchronous rotation. The moon's rotation rate is the same as the orbital rate around the Earth. So its sidereal period is about 27.3 days. just as a sidereal day and a synodic day, there's also a sidereal month and synodic months for the moon, and we talked about those already. So that's a little bit about how the moon works. Okay, let me talk just a little bit about tides. So you remember Newton's formula for gravity, right? And so I'm gonna go back to that for a second. Newton said the force of gravity is this constant g times the mass of one object times the mass of the other object divided by the square of the distance between them. And so I'm just going to talk about how that creates tides here for a minute. And so let's pretend this is a planet or a moon or something like that, some big object, and this is a bunch of little objects. You can imagine these as like basketballs or billiard balls or something like that. Since the formula for gravity has distance in its denominator, if all these guys have the same mass, then if I call this one m1 and each one of these in succession m2, then this planet m1 is pulling harder on this guy than on this guy because the numerator is the same, assuming they're all the same type of basketball, but the denominator is larger for the farther away ones successively. And so this planet is going to pull harder on the nearby guy than on the middle guy, and harder on the middle guy than the faraway guy. The effect of that is to pull this piece apart. And so this guy gets pulled hard, this guy gets pulled less hard, and this guy gets pulled less hard. And that effectively kind of tries to tear these guys apart. And so this is what, by the way, this effect is why the moon doesn't rotate relative to the Earth. It keeps one face towards the Earth. The Earth stretched the moon out and then kind of locked it in. Well, the moon's doing that back to the Earth now. So if I draw here, here's my Earth, right, and here's my moon, again, not to scale. The moon's pulling harder on this side of the Earth than it is on this side of the Earth. And so if I have an ocean here, the solid part of the Earth doesn't flex much under that, but the oceans are just liquid. And so the oceans just kind of bulge out on this side because this side's getting pulled harder, and they get left behind a little bit on this side. And so that's what the oceans do in the direction of the moon. And so you would get high tide here, and then low, and then low, and then high. So, you know, if you're standing here, right, then if the moon is over your head, you have a high tide. If the moon is on your horizon, either horizon, you're in low tide. Or if the moon is through your feet, you're back in high tide again. So over the course of 24 hours, you go from high tide to low tide to high tide to low tide to high tide. Now it's not quite that complicated because, like we talked before, the Earth is orbiting. The moon is orbiting as this is happening, and so it's not quite 4 times a day. It's a little bit less than that. Ancient people who lived on coasts figured out timetables a long time ago. They didn't understand why they happened, but they were very predictable. And it wasn't until Newton came along, one of the many things that Newton did, he applied his law of gravity to understand why this is the way it is. And so that basically explained how tides work. It's nothing is ever perfect in space, and so it's a little trickier than that because it turns out the sun also exerts tides. So So when the sun, earth, and moon make a line, so, you know, let's say here's the earth, right? Let's put the sun over here. I know this is not a scale drawing. So if I put the moon here, or here, in either one of these positions, the sun, earth, and moon are in a line, and I'm going to draw my earth in black here, just for sanity reasons. Right. Then both the moon and the sun are trying to stretch the earth this way. Again, it doesn't matter if the moon's on the same side of the sun or the opposite, because they're both stretching it, right? And so, in this case, we get spring tides. These are just extra large tides. By the way, they're not called spring tides because they happen in the spring. They're called spring tides because they kind of spring up. They're just suddenly extra large. And so they call them spring tides. And these happen about every 2 weeks, right? Because it's halfway through the cycle of the moon's phases. So instead of being here and here, when the moon is here and here, right, now the moon is trying to stretch the earth this way, but the sun is trying to stretch the earth this way, and they cancel out a little bit. And so we get low high tides and high low tides, and that we call those neap tides. For the sake of tests and stuff, that's the story on that. It's a little, the Earth's motion is and the moon and all that is a little more complicated because they're not all in the same lines. I don't want you to go to some vacation spot in Cancun and start asking questions about why you get here at high tide when the moon isn't exactly overhead. It has to do with the fact that the Earth is rotating and how water move in various parts of the world. I think in areas like the Gulf of Mexico, the tides are altered because of how that water is trapped, and in several places on the Earth it's like that. So it's not always simple, but this is a simple view, and if I ask you a question on a test, just keep this view in mind. So here's a slides version of some of those pictures. This is the stronger attraction to the moon for the near part of the Earth, medium and weak attraction for the far part, and so you get this kind of effect. Water flows towards the kind of the center of that attraction, and so you get effects like this one where the boats are in water, or later the boats are on the ground, depending on whether you're at high tide or low tide. And then this is a picture of spring tide on the left and neap tide on the right. So it turns out the moon's tidal effect is about twice as big as the sun's tidal effect. And so the sun's much bigger, but it's much, much farther away. And so those two combine to make the sun's tidal effect a little bit weaker. The moon, as a result of this, is slowly receding from the Earth at a very small rate that's measurable. I forget if it's an inch a century or something like that. It's a small distance per time. It was first postulated theoretically by George Darwin, who is like the grandson of Charles Darwin. He even kind of looks like him there. And it was finally measured with some reflectors they put down with Apollo 11 that you could bounce light off the moon with and measure how far away it is by timing how long it takes the light to get there and back. And so they can make very precise measurements of that and tell within an inch or so how far it is. So now we're going to talk a little bit more about the moon. We're going to talk about eclipses. And so this diagram looks kind of complicated. If you remember back when I was showing you in Celestia that the orbits aren't all quite flat, so here's the sun in the middle, and the white circle in the big square is the Earth's path around the sun. These little slanted squares are the moon's orbit around the Earth. And so Most of the time, when the moon kind of passes between the Earth and the sun, it's either above or below the line connecting the Earth to the sun, and so it doesn't cast a shadow on the sun when it's on the Earth. The moon doesn't cast a shadow on the Earth when the moon is between the Earth and the sun, and it doesn't fall into the Earth's shadow when it's on the far side of the Earth from the sun, because it's not in line for that to happen. And so most of the time that's how it works as the Earth goes around the sun. Occasionally, however, these two planes cross, then if the moon is right between the Earth and the sun, where the line where the two planes cross, in other words, the plane of the moon's orbit and the plane of the Earth's orbit, on that line, which is called the line of nodes, the title of this slide, when the moon is between the Earth and the sun, then now it is lined up to cast a shadow on the Earth. And so if the moon casts a shadow on the Earth, we get what's called a solar eclipse. And if instead the moon is on the far side and the Earth casts its shadow on the moon, that's called a lunar eclipse. Notice that the shadow cast by the moon on the Earth is really tiny. It just covers a tiny section of the Earth, whereas the moon is completely eclipsed in the Earth's shadow. And so only the people who are in the shadow during a solar eclipse, who are in the moon's shadow in a solar eclipse, get to see the eclipse. But in a lunar eclipse, the whole half of the Earth that's facing the moon, anybody can see it. And so lots more people see lunar eclipses than solar eclipses. In case I forget to tell you later, the next solar eclipse in the United States is April 8th, 2024, and you should stop what you're doing and go see it. It's going to pass through Oklahoma and Texas, and it is a life event. There's only going to be maybe one more this century, and it is a cool thing to see. We saw the one in 2017, and it was spectacular. So it's not just for science nerds. I give these the mom test. My mother had no interest in science, but she would have loved seeing this. So, okay, so let's talk a little bit about what happens there now. So first of all, let's just talk about shadows, right? And so if you look, so here's the sun, and let's say this is the Earth here, or the moon. I said it can be any spherical body. So here, let's call this the moon, right? This blue thing. If you're in what's called the umbra 1, then if you're back here, you can't see any of the sun. You're in what's called the umbra, which is the darkest part of the shadow. That's what the umbra means. If you're in the darkest part of the shadow, that's the umbra. If you're in the umbra, you can't see any of the light source. However, if you're in what's called the penumbra, like let's say we're in region 2, so this is what you see in region 1, right? Box 1. In region 2, you see part of the sun in this region up here, but I guess it's position 2. You see part of the sun, but not all of it. Same thing with position 3, also in the penumbra, but it's closer to the border, so you see more of the sun. Finally, if you're in position 4, also still the penumbra, meaning that you can see some of the sun. There you would see an annulus, a ring around the sun. If you're far enough away that the sun appears bigger than the moon, then you'll see what we call an annular eclipse. So this is the geometry of a solar eclipse. Once again, a lot is happening here, right? First of all, the moon is orbiting the Earth while this is going on. Second of all, the Earth is rotating while this is going on. And the moon is casting a shadow on the Earth. And typically that shadow might be 30 miles in diameter, something like that. And so all this is happening, and there we get what's called an eclipse path, which is the path of that solar eclipse shadow. And so the people who are right in the umbra get what we call a total solar eclipse. And depending on if you're in the center of the path, you might get a few minutes. If you're on the edge of the path, you might get a really short period of time, just a few seconds. something like that. You might just get what we call a penumbral solar eclipse, which is what we had in Oklahoma in 2017, where it doesn't block out the whole sun, it just blocks out part of it. So that's what during a total solar eclipse, you get to see the corona. That's the outer layer, that's the outer atmosphere of the sun. Normally you can't see it, but it's beautiful and it looks like that. If you were in the, you could get, so this would be, let me see if I can get back to these right. So this guy here, position 1, would be a total solar eclipse. Position 2 and 3 would be a partial, and this would be called an annular solar eclipse. Now, you go through partial phases while you're getting to total, but sometimes you may never get to total because you may never be in the part of the shadow of the Earth where you're in the umbra. And so lots of eclipses are just partials. Let me just pull this one up. So this was the 2017 solar eclipse, and we saw it in Wyoming, and we were right down the center line, and we had about 2.5 minutes of totality. And the shadow of the sun trekked across the Earth at about, I think it was about 1,700 miles an hour or something like that, which means it took about 2 hours to get across the United States. We did some little experiments to measure its speed, but it went to totality and got pretty dark, and then so we could see stars in the daytime and things like that. The next one's going to have a path, I think, this way from Texas up through the northeast, if I remember right. And it's going to cut through southeastern Oklahoma. And you should plan on taking a day off work and bringing your kids if you have any, or your relatives. So the other kind of eclipse is called a lunar eclipse. And here's a picture of a lunar eclipse. A lunar eclipse is the moon passing through the shadow of the Earth. And like I said, we're going to have one of those on the 26th of May, or we had one on the 26th of May by the time you watch this. And there are several different ways of describing those. It's called a penumbral eclipse if the moon only passes through the Earth's penumbra. It's called a partial eclipse if part of the moon passes through the Earth's umbra, but part of it remains in the penumbra. And it's called a total lunar eclipse if the moon passes through the Earth's umbra completely. And so those are the most fun to see. Totality is the most fun to see because it has, the moon will look red, and that's because, for the same reason, they'll call it a blood moon, for the same reason the sunset looks red, a total lunar eclipse will look red because the light that does get through is scattered around the edges through the Earth's atmosphere. And any light that gets scattered through the Earth's atmosphere from horizon to horizon ends up being red because all the blue gets filtered out of it, for the same reason that our sky looks blue and sunsets look red. And so the light that gets through is red, and so you'll see a blood moon. They'll call it a blood moon. A total lunar eclipse will look red. Those can often last for an hour or something like that, because the Earth's shadow is so much bigger on the moon than the moon's shadow is on the Earth. So again, a lunar eclipse is seen by everybody on the side of the Earth that can see the moon, whereas a solar eclipse is only seen by the people in the shadows. So many, many more people see lunar eclipses than solar eclipses.